Okay, so for the first part, in this part, we aim to encourage you to rethink the clinical value and the utility of PGT. So you will hear how we leverage SNP-based approach to provide insight into Euploid, as well as how we utilize RNA from T sample combined with AI to predict implantation potential. So we will also cover the development of an PGT-A, and we are pleased to have a friend from Spain who will share the valuable experience and perspective on the clinical significance of the origin of Euploidy. So it's my pleasure to invite the first speaker, Dr. Taoli Ding from Yikon Genomics. Dr. Ding received his PhD in biomedical engineering from Peking University and currently serves as the Associate Research Director at Yikon Genomics, where he leads the development of PGT, which is one of the Yikon's core area of expertise. So today, Dr. Ding will guide us in rethinking Ploidy and introduce a unified SNP-based multi-omics approach to PGT. So please join me to welcome Dr. Ding.
Thanks, Tim. Thank you for the introduction. So we all work hard to select euploid embryos for transfer. But is it enough for a successful pregnancy? Today I will share the answer. The answer is no, and I will show you why the answer is no, and introduce a unified SNP-based and multi-omics approach to PGT, so which is far beyond the euploidy and aneuploidy. Let's begin with something we know with PGT-A. PGT-A works. High-quality meta-analysis suppose that PGT-A through euploid embryo selection increases the live birth rate, ongoing pregnancy for embryo transfer, and the implantation rate. And at the same time, it lowers the miscarriage rate. So PGT-A is a real game changer, but it is not the end of the story. Look at these numbers. So with euploid embryo transfer, the clinical pregnancy rate ranges from 48 to 65% across all populations, and the live birth rate ranges from 41 to 62% across all the populations, and the miscarriage still happens in about 8 to 15% of the euploid embryo transfer. So euploid embryo transfer doesn't yield a 100% implantation. So the euploidy can't fully account for the differences in the pregnancy outcome. So why? How euploid embryo can have a live birth? So there seems like a black box between the euploid embryo and the live birth or pregnancy. So when we opening the black box, there are too many factors that affect the implantation. I grouped them into 3 categories. First, embryonic factors, including heteroploidy, such as triploidy, UBD, CNV syndromes, like microdeletions and microduplications. Then mosaicism, false negative or false positive or mosaic CNVs lead to embryo waste or misdiagnosis. And then multi-omics, including epigenetics, transcriptome, and proteome, and so on. These are embryonic factors. Then the second is endometrium, including endometrial receptivity and immunity and microorganism. So we all know the implantation window play important roles in the implantation, as well as the dialogue between embryo and the endometrium. And also the immune regulation plays important roles in the implantation. And if the microenvironment is dominated by the lactobacillus, so the implantation will be easier. And the third factor is hormones and nutrition. including maternal endocrine, like HCG and so on, and heavy metals, endocrine disrupting chemicals, folic acid, vitamin B12, and so on. So all these factors affect the implantation. Today, I will focus on the embryonic factors that we can detect in the next generation PGT. One exciting direction is multi-omics. So we separated the nucleus and the cytoplasma to conduct DNA-seq to obtain a CNV result, and RNA-seq to obtain an RNA score. And the RNA score can be used to evaluate the developmental potential of the embryo. And by using this score, using the RNA score, we can improve the implantation rate significantly. So you can see from this figure. So RNA-seq, adding RNA-seq gives us a much clearer picture about the variability of the embryo. We collaborated with our partner and published the paper. Tomorrow at 4:50, Professor Chong will share the more detailed data about the combined DNA and RNA sequencing. So welcome to follow. Now let's come back to the PGT-A. We have a PGT-A Upgrade solution. It is utilized the chrominist kit based on the mosaic technology. And the feature is with one tube, one library, we can realize the detection of PGT-A basic and upgrade. And it is compatible with major sequencing platforms, including Illumina and GI and GenMine. And within, it takes only about 2.5 hours to finish the library preparation. And we use 3 million reads to obtain a good CNV results and SNP informations. So in addition to 4 megabase resolution and sibling QC, we can also get more than 40 kinds of CNV syndromes. The detection of microdeletions or microduplications smaller than 4 megabase. And we also can perform Ploidy check and false positive mosaic CNV recognition. So it's a really great upgrade. This figure shows the whole genome amplification process of chrominist kits, just with one tube and only 2.5 hours to finish the whole process. So now let me show you why the Ploidy check is important. Because for conventional PGT-A, it only shows a simple result, like 46XY. But what if the embryo has a maternal UPD or a paternal triploidy? So these abnormalities comes from abnormal fertilization or abnormal oocyte segregation. Once happened, triploidy will cause failure in implantation. But these informations are missed by PGT-A, by conventional PGT-A. And we provide comprehensive PGT-A upgrade to include Ploidy detection to fill this gap. So this is the principle of how we detect the Ploidy. At a given SNP locus, we may get a AB pattern. AB pattern means the embryo inherits one allele from the mother and one allele from the father. So at this given SNP locus, it is balanced. But for UPD, the 2 alleles comes from the same parents, so the 2 alleles are totally the same. And for trisomy or triploidy, there are 3 copies of the alleles, so we can see different symbolosis. So we can inference haploidy be based on the SNP allele combinations across the whole genomes. And we applied this method to clinical data, clinical sample. We collect clinical data from 77 centers, and covers more than 40,000 embryos. And between them, among them, about 46% are normal, are euploid, and 39.75% are aneuploid, and about 12% are mosaic. Please notice that the euploid rate is a little lower than the common level because more than 60% of the patients meet the AMA indication. AMA means advanced maternal age, so the euploid rate is a little low. And there are 1.37% of samples are abnormal euploidy, in which 63% are triploid. So once the triploid was implanted, it will cause failure in implantation. So our Ploidy test will help patients. In addition, we also applying AI into our PGT-A Upgrade to enhance its performance. We all know AI is developing rapidly and it is transforming our field. So AI, we can treat AI as a powerful analytical tool. It uses advanced machine learning algorithm to help us to process the data. Publications highlight how AI can analyze the time-lapse videos and the genomic data to promote the accuracy and the efficiency of data to predict the embryo. So we are now integrating AI into our PGT-A Upgrade pipeline to improve both the accuracy and the efficiency, especially for mosaic detection. And without AI, actually, we have already developed a powerful method named or called pH trees. This diagram shows the principle. So at a given SNP locus, if the paternal genotype is 0, 0, and the maternal genotype is 1, 1. So in theory, the embryo at this site should be 0, 1. The value, the variant allele frequency should be 0.5 at a normal condition. Yeah. But affected by the bias caused by the copy number variation, the VF value may be bigger than 0.5. So that means that indicates a maternal bias. And if the VF is smaller than 0.5, it means it indicates a paternal bias. So using the millions of SNPs across the genome, we can calculate an uneven score. So if the uneven score, the value of an uneven score is 0, it means there is no bias to paternal side or maternal side. And the CNV is a false positive one. And take this sample as an example. Like this, there is a duplication on chromosome 1, and it is a paternal bias. So this duplication comes from the paternal side. So that's a clinical example. And we collaborated with our partner and published a paper about the CNV origin analysis. And this study demonstrates that CNV origin analysis help reduce the false positive CNVs. That means a lot of more patients will have a chance for a transfer, for a euploid transfer. Professor Lin comes from Women and Children's Hospital of Chongqing Medical University, will share her poster. So welcome to follow this poster. Now we have a standard answer for our AI training, and we also have copy number data and SNP data. So totally we constructed 121 features. These features integrate like genomic signal statistics, quality control metrics, spatial signal patterns, and the log likelihood ratio evidence to evaluate mosaic CNVs. And this bar plot shows how these features affect the output of the AI model. This multidimensional feature set provides a rich representation of mosaic CNVs, enabling the AI model to learn subtle patterns that are often missed by the conventional PGT-A. So this is the AI model performance on test side. You can see the ROC curve demonstrates excellent discriminative power with an AUC 0.95. And more importantly, as the TP level, as the true positive level decreases from 100% to 95%, the reduction rate increases from about 2.3% to 63%. That means we can rescue more than 2/3 of embryos back because we can reduce about 2/3 of the false positive CNVs. So this flexible trade-off allows us to choose the best fit threshold that for our needs, fits our needs, maximal safety or high efficiency. We can just choose. And then we also perform validation about the microdeletions and microduplications detection. We tested about 132 samples, including standard cell lines that are past cells with non-CNV results. And we also include embryos from PGT-M. Whether the embryo carries microdeletions or microduplications is confirmed by SNP linkage analysis. So we also have a standard answer. And the detection performance is 100% sensitivity and 100% specificity. Now let me give you a true clinical case. So the target CNV syndrome is this one, 1.4 megabase microdeletion. It is non-CNV syndromes. So in this category, there are 4 embryos, embryo from embryo 1 to embryo 4. And we successfully detected the microdeletions in embryo 1 and embryo 3. And we successfully reported no microdeletion in embryo 2 and embryo 4. So the result, the CNV results is 100% consistent with the SNP linkage analysis. And now this performance is available for our PGT-A upgrade. So at last, let me have a summary. First, PGT-A effectively improves IVF outcomes by selecting euploid embryos. But euploid embryos alone can't guarantee 100 implantation, clinical pregnancy, and live birth. The implantation failure of euploid embryos is associated with multiple factors, including heteroploidy, CNV syndrome, mosaicism, misdiagnosis, and so on. And our mosaic-based PGT-A upgrade achieved 1-tube detection with 4 megabase resolution. And Ploidy check CNV syndrome screening and mosaic false positive recognition within 2.5 hours of library preparation. Our clinical data from 77 centers shows 1.37% Ploidy abnormalities. 63% of them are triploidy, which are missed by basic PGT-A but detectable by the upgrade solution. We also use AI and parental origin analysis help reduce false positive mosaic codes. And the PGT-A upgrade achieves 100% sensitivity and specificity for microdeletions and microduplications detection across 132 samples. Well, finally, we are developing more PGT technologies and launching more clinical studies with our partner. So I warmly invite you to join us. Together, we can make PGT better for every embryo, every family. Thank you for your attention. attention. Thank you.
The floor is now open for questions. 欢迎大家提问跟讨论。
Any questions?
Good evening. Good afternoon. So it was a nice lecture, a good information that we can carry. One understanding I need to get from the RNA score, which genes you are looking into to mention as or to score for the potentially viable or the live birth rate with the RNA score? How many genes you are targeting, or how you are evaluating to mark as a more viable embryo or getting the live birth rate? You are giving the RNA score with the RNA-seq.
没有太听清楚大家。
问有多少个鸡？
哪个
？Vera，对。
Vera. So about there are many markers actually, but we only choose about no more than 10 markers at the last. Yeah. The training model we tested many of the features, many of genes, but at last we used actually not too much.
Actually, maybe Dr. Zhou want to address that question because she's the one that is actually leading this research.
Yeah, actually, we use whole transcriptomics sequencing to get the gene expression, and then we do the machine learning, something like that. We do the feature selection, and we also do the feature selection from the public dataset. We use the biological understanding of the embryo implantation process. So at the end, combine our experimental or clinical sample data, we finally got the more than 400 genes into our model. But we use the pathway level, the feature to measure the embryo implantation, because every gene expression will be sensitive to the environmental noise, like the embryo culture, they will affect the gene expression. So we, because of that, we use the pathway level scores, combine many types of genes together to address the implantation potential. So after that, maybe more than 10 features, pathway level features together to evaluate the embryo competence or embryo implantation. Yeah, thank you.
Basically, long story short, more than 400 genes categorized into 10 different features. Any other questions?
Thanks, really nice talk. I just wanted to understand how close we are to kind of, you've got your euploid embryo and now you've got these additional features. How close we are to sort of ranking them, because the past 10 years has been about throwing away embryos or ignoring embryos because they looked abnormal, mosaic. And now you're saying include them back in again, but how do we rank them based on some of the data you've shown?
You mean the RNA score or something else?
Well, everything.
Test?
You've got all these lovely new features. You're using AI to reduce the false positives. So in a clinical situation, somebody has to say, well, which one will I transfer first? Right? So I'm just asking, based on your data, how you would give recommendations for that.
Yeah. So in addition to the conventional copy number variation informations, we also have a Ploidy check. So at first, we need to check the Ploidy. If the embryo is triploidy or UPD, we need to pass them at first, and then we can just check the mosaic. If there are euploid embryos, we can use euploid embryos at first, of course. But if there is no euploid embryos, we have to use a mosaic embryos. So if you use our AI model, you may can distinguish which mosaic may be a true, which mosaic is false. And at that condition, you can choose the false mosaic embryos to transfer. Yeah. And of course, there are also microdeletions, microduplications. We have a list of more than 40 kinds of microdeletions or microduplications. The embryo shouldn't have the CNV syndromes at this list. Yeah. So it is a multi-dimensional assessment about the embryo. Yeah.
Thank you.
Thank you.